Good afternoon, everyone. Thank you for joining us today and welcome to the BDTI Ski Studio. Our topic for today's session is predictive modeling and real-time analysis, forecasting and monitoring bikes in Paris, which is a very interesting and concrete topic nowadays. Here is a quick overview of the agenda of today's session. So first, we will provide an introduction to what BDTI is. Following that, we will dive deeper into the workshop content. After the workshop, we will open the floor for a Q&A session. And finally, we will wrap up with a summary of today's session and next sessions that are going to happen in December. Along the webinar, feel free to share your thoughts, ask questions in the Q&A section. And for asking questions, please click the three dots on the right to see the Q&A section. Now I will hand the floor to Maria Claudia, who will provide an overview of BDTI.
Thank you, Aurora, and hi, everybody. I'm very happy to see you back. And I would like to spend a few words about this project, where basically we are trying to create this series of webinars and try to share with you interesting inputs, about reusing open data for the public good. So the project that we are presenting is this big data test infrastructure. Probably many of you already know about it. It's in few words, it's a data science playground that is free for public administration, and it's completely based on open source tools. So the idea behind this initiative is to support public servants working in public administration. That could be small, medium, and big ones, getting familiar with the data analytics journey, and also having something that is up and very well known in the market in terms of tools and also capabilities. The infrastructure is completely developed in the cloud, so you don't need to spend your time in order to setting up or tune it to properly use it. It's everything prepared and ready to use. So if we move to the next slide, you can see a very nice summary of the different tools we are offering in this big data test infrastructure. And you can see, if you are a bit familiar with the topic, that they are very popular in the data world, and most of them are also from important, let's say, players like Apache. In this case, we have a different database, but also we have tools like Apache Superset, and also we are covering different functionalities from collection to visualization. All of them are open source, and that's also why we are, let's say, insisting on this point, because all the webinars we are developing together with you are easily reproducible. You can do the same things we are going to do together on your own notebook. So the only thing that is needed is that you need to have these tools, and then you can reproduce the exact same steps that we are developing together. Then if we move next, just to remind and to underline the fact that this infrastructure is for public sector, so basically for public administration, but also for people that are keen in supporting them. That's why we are always trying to push for a partnership between students, maybe from PhD programs or master's programs, to support the public administration. It could be their municipality or maybe a specific department, in order to move forward with a data-driven use case for the public good. If we move next, these are just few of the most interesting use cases you can find in our website. It's very, I would say, insightful, the fact that we are trying to cover different domain areas, but the most popular one is always urban analytics. So we see a lot of interest from cities and from municipalities that are applying to the project, to this big data test infrastructure, because they really want to analyze and to understand a bit better some challenges they are facing in the field of urban mobility. And this could be traffic management, a better distribution of public transportation. And specifically on this topic, we have, for example, our Naples in Italy, we have Turku in Finland. They are analyzing mobility, let's say, data. And also we have other similar topics like analyzing traffic incidents and also understand how you can improve the city around these topics. All of these pilots are documented in the website, so this could be an interesting material for you, maybe to have some inspiration. Then, thank you. This is the very, I would say, light process we are following. So in case you are a public administration interested in applying for this initiative, what we always recommend is to have a look to our website. You can find a lot of resources. And then you can also find this pilot request, that it's a document that is basically the content of your pilot. So this is going to be submitted, and then in a few days we are going to review this pilot request, and hopefully we are going to set up a meeting with you in order to deliver the platform and to be ready to start developing your use case. Feel free to check the monthly newsletter. And also feel free to share with your colleagues or with your, I don't know, friends that are interested in data for good, all these resources, because they are really useful. Thank you. If we move next, exactly, now it's time to go deeper in the most interesting part of this webinar. We are going to analyze open data, real-time data about bicycle use in Paris. And as always, all the code we are developing, and also the recording, will be available in open source under our webinar probably tomorrow morning. You can go in our website, you can fork the repository, and you can really start learning and reproducing the same code behind this use case. So thanks again, and now I give the floor to my colleague for the workshop. Enjoy the session.
Thank you, Maria Claudia. Welcome everybody, and thank you for joining this workshop on this predictive modeling, where we will work through the case of forecasting and monitoring of bicycle use. Today we will explore how open data, open tools, and forecasting can provide powerful insights for urban management, especially for public administration, as Maria Claudia has been sharing with us. Let's first understand what forecasting is, what we mean by that. In simple terms, forecasting is the process of predicting what will happen in the future based on the past data. When we talk about time series forecasting, we are looking specifically at data that's collected over time, like traffic patterns, weather data, or even economic indicators. Now, why is forecasting so important, especially for public administrations? Well, here are a few key reasons. The first place, to get informed resource allocation. By predicting future needs, public administrations can allocate resources more effectively. For instance, if we know traffic is going to spike during certain hours, cities can schedule road maintenance or adjust public transport accordingly to better serve their residents. Second option would be for proactive policy development. Forecasting helps policymakers anticipate future challenges and opportunities. For example, if air quality data shows a trend of declining air quality during certain seasons, that can inform environmental policies aimed at improving public health. For enhanced emergency preparedness, when it comes to emergencies like natural disasters or public health crises, forecasting can provide critical insights. This helps administrators plan and respond more effectively, potentially saving lives and resources. Also for improved public services, analyzing trends in how people use services like public transportation or waste management, for example, allows administrations to enhance service delivery. When they understand what residents need, they can adapt and improve those services. And finally, for a community engagement. When public administrations share forecasting data with their community, it builds trust. People are more likely to support decisions when they understand the data driving them, leading to better collaboration between the public sector and the community. In summary, effective forecasting and time series analysis equip public administrations with valuable insights that help them make informed decisions. By leveraging historical data, they can create more resilient and responsive systems, ultimately improving the quality of life for everyone in the community. Now that we've covered what forecasting is and why it matters, let's talk about understanding the data itself. This step is crucial because the insights we derive from our data can reveal hidden patterns and trends that might not be immediately obvious. When we look at the time series data, there are several key elements to consider. The first is patterns, recurring behaviors in the data over time. For instance, bike usage might peak in spring and summer, indicating seasonal trends. Trends, the general direction of the data over time. Whether bike usage is increasing, decreasing, or stable, recognizing those trends will help planning for future changes. Seasonality, as mentioned, periodic fluctuations at irregular intervals, such as daily or weekly. For example, bike usage might spike on weekends when more people are out. Anomalies, outliers that don't fit established patterns, indicating unusual events. It's key to identify these outliers because it helps ensure the forecasts aren't skewed by one-off occurrences. And relationships, how different variables interact with each other. For example, how do weather or local events affect bike usage? Understanding those relationships enables more nuanced models. By diving deep into the data and uncovering those hidden insights, public administrations can gain a clear picture of what's happening in their communities. This understanding is essential for making informed decisions and crafting effective policies. Ultimately, the more we know about our data, the better we can forecast and respond to the needs of the public. As we dive on the practical use case today, I want to encourage you to think about the various applications of forecasting in your own context. Forecasting is not just a theoretical exercise, it has real-world implications that can drive decision-making and improve services across different sectors. So, reflect on your own experience. Consider the challenges that you face in your respective roles. Are there specific areas where you think data-driven forecast could help improve outcomes? For instance, think about traffic management. How could forecasting demand for public transport or bike-sharing services enhance urban mobility, as we'll see today? Public health. In what ways might forecasting help allocate resources during seasonal flu outbreaks or public health campaigns? Environmental planning. How can predictions related to air quality or noise levels could help in policy decisions in urban development? Also identify opportunities for improvement. As you watch the demonstration, note down any ideas that come to mind regarding how similar forecasting techniques could be applied to other datasets or challenges that you encounter. Consider what specific data do you currently have access to that could benefit from analysis and forecasting. Are there existing reports or projects in your organization where forecasting could add value or improve accuracy? Think beyond the workshop. Forecasting isn't limited to a single use case. It's a versatile tool that can adapt to various scenarios. As we go through each step of the workshop, think about how could the concepts we discussed today be applied in the different contexts within your municipality or organization, or what additional factors, local events, or seasonal trends might you need to consider when applying these forecasting methods to your own data. In the end, we're having a Q&A session after this demonstration, and I encourage you to share your thoughts and ideas. If something sparks your interest or you have a question about specific application, don't hesitate to bring it up. Engaging in this discussion will enrich our collective understanding and help us explore how can we utilize forecasting effectively in our roles. By considering these applications, you will not only gain a deeper understanding of the techniques we'll cover today, but also how they can empower you to make informed decisions in your day-to-day operations. Let's keep the conversation going as we move through the workshop. And now it's time to go to our specific use case we'll do today. Now that we've seen the importance of the data analysis and forecasting, the question we will be solving today is how can Paris enhance urban mobility and promote sustainable transportation by comparing forecasted and actual bicycle traffic data. Throughout the session, we'll be using open data sets from the Paris Open Data Portal, which offers a wealth of information on various urban aspects like public transport, tourism, culture, and more. Before that, and to reinforce the message from Maria Claudia, we want to reinforce the importance of the open data. Open data refers to freely available data sets that anyone can use, modify, and share. This concept is especially relevant for public administrations, as open data fosters transparency, collaboration, and innovation. Governments around the world are increasingly releasing their data to the public, enabling researchers, business, and citizens to develop solutions to urban challenges. In this workshop, we'll be working with Paris bicycle count datasets. These datasets are publicly available, and you will see how we can access, analyze, and visualize this information to derive valuable insights. The importance of open data cannot be overstated. It provides a foundation for transparency and community-driven innovation. Not only does it offer an opportunity for cities to improve their services, but it also allows the private sector and civic tech communities to build on this data to create smart, data-driven solutions. Additionally, there are millions of open data sets available through platforms like data.europe.eu. This European-wide portal hosts data from various sectors and regions, covering topics from environmental sustainability to transportation, public health, and more. These datasets are free for reuse and can empower public administrations to improve urban planning, resource allocation, and policy development. For these workshops, as I mentioned, we'll be working with two main datasets. The bike counting history. This is an historical data set of hourly bicycle counts and location of counting sites. The city of Paris has been deploying permanent bicycle counters for several years to assess the development of cycling. And the hourly biking counting. The data set of hourly bicycle counts by counter and location that counts so we have the data of the counting sites on day -1 for the last 13 months. A counting site can be equipped with one counter in the case of a one-way cycle facility, or two counters in the case of a two-way cycle facility. We'll be getting that data through an API, and we'll be using for our use case. As we move into the practical portion of this workshop, it's essential to familiarize ourselves with the tools that we'll be using. Each of these tools plays a crucial role in our workflow, allowing to efficiently analyze data, create visualizations, and share our findings. Today, we'll be using MongoDB. Mongo is a NoSQL database designed for storing and managing unstructured data. It allows for flexibility in how we structure and query our data, making it an ideal choice for dynamic datasets. In our case, we'll use MongoDB to store and retrieve bike count data collected from an external API. This will enable us to efficiently manage large volumes of data over time and provide a structured way to analyze trends in bike usage. We'll also be using RStudio for our R scripts. What is it? RStudio is an integrated development environment for R, a programming language widely used for statistical computing and data analysis. RStudio offers a user-friendly interface that supports script writing, data visualization, and package management. We'll leverage RStudio to write and execute R scripts that perform data analysis, including fetching the data from APIs, cleaning and processing the data, and building forecasting models. RStudio simplifies the coding process, allowing us to focus on analysis rather than technicalities. We will also be using R Markdown. R Markdown is a document format that enables users to create dynamic reports that integrate code, output, and narrative text. It allows you to combine analysis and documentation in a single file that can be rendered in various formats such as HTML, PDF, or Word. We'll use our Markdown to document our analysis and results in a clear, reproducible format. By knitting our R Markdown file, we can generate polished reports that include both code used and the results produced, making it easier to share findings with stakeholders. Here's a brief overview on what we will cover today. We will be setting up our BDTI environment. We'll begin by logging into the BDTI platform, and deploying the necessary services, including RStudio and MongoDB. This will provide the foundation for our analysis. Once our environment is set up, we will explore the byte count dataset, identifying key patterns and trends that will inform our forecasting model. In third place, we will write our scripts to fetch byte data count from the external API and store it in MongoDB. This step is crucial for ensuring we have access to the most up-to-date information for our analysis. We'll build the forecasting model using the XGBoost algorithm. We will develop a predictive model that forecasts byte counts for the upcoming week. We will cover key concepts like feature engineering, model training, and hyperparameter tuning. We'll be visualizing our results after generating our forecasts, and we will visualize the actual versus the predicted byte count, allowing us to evaluate the model's accuracy and performance and gain insights into byte usage trends. Finally, we'll discuss how to automate this process for ongoing data collection and forecasting using tools like Mage AI and Apache Airflow. This will help ensure that our forecasts remain relevant and up to date. To ensure we have enough time to cover everything thoroughly, we've pre-recorded the demo with my colleague Berta. This allows us to focus on each step in detail without rushing, but don't worry, we are still here with you throughout the session. While you're watching, feel free to ask any questions that come up. My team and I will be actively responding to your queries in the chat as the demo plays. And we will make sure to address anything that needs further clarification in the Q&A. After the demo, we will have that Q&A session. We will dive deeper into any part of the process or tools that you're curious about. So without anything else to add, let's get started with the demo. Watch closely and don't hesitate to reach out and cut off any questions.
All right, so let's get started with setting up the environment and tools we'll be using for this use case. So the first thing we'll do is log into the portal and deploy the services we need for the analysis. So I'll go over to the BDTI website here and click on the BDTI portal, access and enter the credentials. And then from the service catalog, we'll find the tools that we need for this use case. So the first one we will need is RStudio. So let's find it here and click Launch to configure it. As we saw in the previous workshops, the naming convention is to give the name of the tool, dash, and the initials of the person who is creating the deployment. That's so when we later share this instance with other people in the group, we know who has created it. So in this case, there will be RStudio, dash, and the initials. We'll make this shared so the people in the ClearPix group can access it. And in this case, we only need a small configuration for CPU and memory resources. We can enable the multi-user if we want to create automatically some other users and passwords. In this case, we'll use the default username and password. And select the NFS, which is the shared storage that we're going to be using. It will be the only one we have. And click Launch to create the deployment. After a bit of time, this deployment will appear in my services, and we can retrieve the password and username from my data. But for now, this will take a few minutes, so let's just keep creating the other deployments. In this case, we only need MongoDB, so let's launch this. We'll use it to store the data that we're going to be using. So we'll put in the name, dash, and the initials. We'll make this shared for the same group and also a small configuration. We see that this automatically fills the CPU and memory resources. And then we need to give it an admin username. We can say user1. The password is automatically created. And again, we can retrieve it later from my data. And that's also just click Launch. So after a couple of minutes, we can see in this My Services page that the RStudio deployment has been created and now it's active. So we can open it and sign in. We will need the username and password in my data. So look here for the deployment, RStudio. Let's check the username and copy the password. And sign in. Okay, now that we have accessed RStudio, what we can do is to create a folder for our project. We'll go here on Files in this section and click here. We can name the folder anything we want. Let's do an example folder, okay. And now we see that this appears here. This is part of the shared NFS storage that we selected in the beginning of when we were setting up this deployment. So if we terminate this deployment, we will still have access to these folders. And all of the people in the group also have access to this. So before we dive into the main analysis, it's essential to understand what R Markdown is and how it fits into our workflow. So R Markdown is a powerful tool that will allow us to write text, integrate the code in R, SQL, Python, and then generate dynamic documents that can combine the narrative with the results. And we can generate these reports in various formats, including HTML, PDF, and Word from the same source file. So it's highly useful for reproducible research and reporting, and as it combines the data analysis with the documentation seamlessly. So in RStudio, working with R Markdown is pretty straightforward. We'll just create a new file. So you can go here on Files, New File, R Markdown, or from here, just click this arrow and select R Markdown. You can give it a title, the author, the name, or use current date when rendering the document. So each time we render the document, it will be updated. And then we can select the output format. We'll use HTML and click OK. So how this is structured is just the first initial YAML section. This header contains the metadata about the document, such as the title, the author, if we had included that, the date, and the output format. And then we have the text and code. So in an R Markdown file, regular text like this is written in Markdown format, and code is enclosed in chunks like this one. So you can select R to create an R chunk, or click here and include on any other type of chunk. So if we select Python, this is now a Python chunk. So when we need an R Markdown file, RStudio runs all the code and the chunks that are in this document, and then collects the output and generates a final document with the text, code, and results. So let's say here we create print hello world. We can run this directly in this section if we're experimenting. So we see the output here. And if we choose to need the document, so to render it, we'll name entitled output and put it in the example folder. We'll save this. Now it's knitting. Let's delete this. Let's hit it again. Okay, now it's knitting, and we see that this is the HTML output. So we see the metadata, like the title, the date, then the text. So the Markdown text that we included, the chunk of code in R that we created, and directly below the chunk of code, it's output. And in the automatic example that when we create an R Markdown file, RStudio fills with examples some parts. So we can see that we can also embed plots like this one. We can close this now and close this one. So now we'll be working with this bike forecasting folder. You have available all of these files in the Skills Studio's GitLab repo. So let's start with the data exploration and open the our markdown file that we have. We automatically get a message that some of these packages that are needed for knitting this document are not installed. So we'll just click install here and it will automatically do this for us. There's other options to do this that we'll see now. For example, we can go to Tools, Install Packages, and look for the packages that we need. So if we need this one, we select it and install. We can also go in this section here on Packages, click Install, and again do the same thing, look for the packages to install. Or we can go either on the console or create a new R chunk and look for and execute install.packages and the package, the name of the package that we need to install. Obviously, the easiest way is just if we have the R file ready, we can just click install on the message that automatically pops up here. So here's our markdown. We see here again the metadata in the YAML section, YAML header. Then we have included some extra style options. These are 100% not needed. Then we can set the global options. We have set some options for knitting that just don't include the cache, don't include the warnings when we need the document. But we have hidden this from the output, so we include equal false. Then we have some text, and then we're going through each chunk of code and explaining what it does. So just so it's easier to see, we'll go through the exploratory data analysis with the knitted output, so on the HTML. So I'll click on knit and we'll see the result. So this might take a while because this is a large document, so we will just have ready here the HTML output from a previous run. We can click on it and view in web browser. And this is the rendered document. So we see just the header, which was here. So the bicycle count forecasting title with the author and the date. We see the text, the introduction, the chunks of code, and some other R code. So we can see it from here. So this table of contents here, we have configured it with this style bit here. Again, it's not necessary to do that. So because of time limitations, we don't have time to go line by line explaining what this code does in the exploratory data analysis part. So just feel free to retrieve this code, and also you will have the knitted output, so this HTML file from the GitLab repository. But for now, we'll just take a look at the general steps. So the goal of this file is to understand if historical data, we can just see if there's any seasonality in the bike counts in Paris or any trends, and also see how the data is structured and all that. So the first thing we need to do is to download this historical data. We're setting or defining where we want to download this data, so the path. Then from where we want to store it. So Paris data already has this URL that we can call for each year, so to systematically fetch the data for the desired year. Then we have seen that the name of the file may change depending on the year, so we just loop through each year and attempt to download the corresponding file. If one of the names is not working, we check the other one. Then this is downloading a zip folder. So we need to extract the CSV files. So this is what this part is doing. And then moving the CSV files to the download directory that we said before. We're renaming the files. And then using the data.table package to read and concatenate all these files into a single data frame. So This will consolidate all the data into one big file, and this will be easier to work with in the future when we want to analyze the data. So we're saving this. And now here at this point, the data is downloaded and ready to see what it looks like. So the first thing we're doing is reading the data frame. We can see with head the first few rows. So we see the different fields, the name, so the name, the counting, the date and hour, etc., and also the coordinates. We have chosen to rename the names of the columns, just so it's easier to work later. And just to have a look how this data actually looks like, we can do a plot. So we can just select a couple of sensors and see what the data looks like. This is what is done here. And then the result of running this is this plot of this ID of counters. So we see the data over time, 2020, 2021, etc. We may already see from this plot that there's probably an outlier here and some strange period here. So we might find that there are counters which are counting zeros for an unlikely period of time, or we assume that that if the count, so if there's no bikes at all in 14 days, then probably the sensor is not working properly. And we don't want to take it into account for our analysis. So we're just finding these counters with 14-day sum with 0 bikes that going through that counter. And then we're removing them, just excluding them from the data frame. So remember, before we had the data, 1 file per year. And now we have 1 unique data frame with all data for all years for all counters. It's probably easier to separate this data depending on the counters, so to have a separate data frame per counter. So this is what we're doing here. And after the preprocessing, we have discarded a few counters. So from the ones that we can assume that they were working kind of all right for all the time periods. We're left with a list of 45 counters. And just to simplify this, we'll just focus on one of them, just because we don't have time to go through all of the different counters, and they're probably similar one to the other. So let's just see the first rows for this counter here. We see where it's located, the date of the counts. So January 1st, 2020, at midnight, there were 7 bikes going through the counter. Then in the following 15 minutes, there were 11, and so on. So we can see all those counts. We can get a summary of the different columns in this data frame for this counter. So we can see that there's some hours, which had a count of 0, and then the maximum number of bikes to go through this counter at a given split of time is apparently 148. Then the mean is 15 bikes. So we're interested in obtaining the number of bikes that go through a given point every hour, not every 15 minutes. So here we basically group it by hour. And then we're plotting how this looks like. So instead of 15-minute counts, we're just looking by the hour for this counter that we selected over time. So it looks like this. And let's zoom in to see the counts for 2022, for example. So it looks like this. We can see that there's some strange periods by beginning and mid of 2020. This is probably and most likely due to the pandemic. So the amount of bikes that were going through the streets of Paris was lower than usual. It's good that we see this in our data. So it means that the data actually reflects things in our society. Then we might want to do some more advanced analysis to see if there's any seasonality. In this case, we have created this plot to group the hourly count for each day by month. So we will see the hour of the day and the count at each hour of the day. So here we have the plot, and we can see the hour of the day on the x-axis and the count in the y-axis for each month. So we see that in May, the peak hour was probably here in the end of the day. This is probably 6 or 5 in the afternoon. Then it's lower in the mornings or during the night. And then we can see the difference by month. So this month has lower counts. This is August, so it may make sense. Maybe less people are commuting because of holidays. Also in the winter months, we can see lower counts. See here in December, we're around peak hour, it's 150 bike counts. Whereas in April or in March, we're getting close to the 200 bikes. So this can, again, explain some seasonality. So next we have created another plot that we're doing here, in which we're going to see the hourly count across all of the weeks. So depending on the hour of the week and per day. So we see that the peak of maximum numbers of bikes is on Tuesdays in the afternoon. It's just pretty high overall from Mondays to Thursdays. Then it goes down on the weekends and Fridays. Again, this is probably due to just being the weekend, less commuters. Same thing happens with the peak in the morning. So this is 8 a.m. We see there's a peak on Monday to Friday, although in Fridays it's smaller. And then on the weekends, there's less of a peak at that time. So we have identified 3 seasonalities, depending on the hour of the day, depending on the day of the week, and depending on the month of the year. So we need to understand when we are developing a forecasting model that these factors may influence, and also other factors and external regressors. For example, the number of people visiting an outdoor swimming pool may be influenced by the weather conditions, such as temperature and sunshine. Gasoline consumption can also vary if there's holiday or there's an economic policy. So these are external regressors. And in this case of bike traffic in Paris, we have identified 2 significant external regressors, which are the COVID lockdown, as we saw in the time series above, and then also public holidays may affect the date. So bike traffic may be influenced by these public holidays. Maybe less people are commuting. So we will include these 2 variables in our future forecasting model. So we'll put a 1 if the day was a public holiday and a 0 otherwise, so in regular days. And this will help us capture how these factors are influencing the bike traffic. So with a solid understanding of data, we now move to the forecasting part of the workshop. We will use R scripts for that, so no more R Markdown. And this will be easier if we later want to automate these forecastings. So now I'll walk you through how we can gather bike count data from an external API, in this case, the Paris Data API, and store it in a MongoDB database for further analysis. And we'll go step by step through the R code that accomplishes this, and I'll explain the key components along the way. So let's go back to our studio here. And in the folder which you have in the GitLab repo, we'll use the initial feed R script. So I'll open it. And again, we get the message that we're missing some libraries or packages. Let's install it. And wait. Okay, so the first thing is we use 3 libraries here. We use HTTR, and this will allow us to make HTTP requests, which we'll use to fetch the data from the API. Then JSON Lite, which is used and is great for handling JSON data. And since the API returns data in a JSON format, this will help us convert that data into a format that R can easily work with. And finally, we use this library Mongolite to connect to our MongoDB database and allowing us to store and retrieve our data. Next, we need to specify which counter we are interested in. And the variable counter ID holds a unique identifier for a specific byte counter in Paris. And this ID will be used to filter our data so that we only fetch records related to this particular counter. Next, we're constructing the URL that we will use to query the API. And it's crafted to access the Open Datasoft API, specifically targeting the byte count data for our defined counter ID. So the where clause filters the dataset to include only records related to our specified counter ID. And the order by date parameter ensures that we retrieve the data sorted by date, which is important for our analysis later on. So next, we need to create a connection with our MongoDB database, and we define the connection details for our MongoDB. The Mongo URL specifies how to connect to our MongoDB instance, including the credentials and the server address. And then the collection name is dynamically created using our counter ID, ensuring that each counter data is stored in a uniquely named collection. MongoDB is a NoSQL database that stores data in a flexible JSON-like documents. And this makes it an excellent choice for our use case, as it allows us for easy storage and retrieval of data without needing a predefined schema for our data. Finally, we insert the data we get from the response to the API. And in the end, once we're done, we disconnect from MongoDB. In summary, this script fetches the byte count data from an external API and stores it into our MongoDB. And this setup allows us to have a structured and accessible way to analyze byte usage over time. So in the next part of our webinar, we will explore how to analyze and visualize this data. So if you have any question about this step, just feel free to ask in the Q&A. So now we're going to see how a second script, which we have named Bike Model, works, and we'll cover key concepts like feature engineering, XGBoost, modeling, and evaluation. So let's open the file, which we named Bike Model. If necessary, we would be asked, like before, to import the necessary packages. So first, we need to load the necessary libraries, some for data manipulation, some for connecting to the database for plotting. And next, what we're doing is connecting to our MongoDB database to fetch our historical byte count data. So this involves specifying our MongoDB connection details, such as the URL, the counter ID, the collection name. And then once connected, this data will be crucial for understanding past byte counts and developing our forecasts. Next, with our historical data in hand, what we're doing is fetch the new byte count data from an external API. So we will construct a new URL that requires the API specifically for our byte counter, allowing us to retrieve the most recent data available. This step is important because it ensures that our model is based on the latest information and improving its accuracy and relevance. After fetching the new data, we will combine it with our historical dataset. So it's essential to ensure that we remove any duplicates and maintain a clean dataset. And this combined dataset will provide a comprehensive view of byte counts over time, which is vital for our analysis and predictions. So next, we move forward to feature engineering. This process involves creating new variables that can help improve our model's performance. For instance, we will generate lag variables here, which represent byte counts from previous hours or days. And these lagged features can capture trends and patterns in the data. Additionally, we can create indicators on holidays and weekends, as these factors can significantly influence byte counts. And by enriching our dataset with these new features, we enhance the model's ability to learn from the historical patterns that we have in the data. So once we have our dataset prepared, we will split it into a training set and a forecast set. And the training set will consist of historical data, while the forecast set will include the data for the next 7 days. So this split is crucial because it allows us to train our model on past data and then test its predictive capabilities on future data, which is unseen. After we have split the dataset for training and testing, what we're going to do is enter the phase of hyperparameter tuning. So we will define a grid of hyperparameters, this tune underscore grid, to optimize our XGBoost model, which is a powerful gradient boosting framework. We will use here the caret package, as I mentioned before, and we will set up a cross-validation to ensure that our model generalizes well to unseen data. And it's vital as this will help us identify the best configuration for our model and to strike the good balance between model complexity and model performance. So we select the best model here, and with our best model selected or determined, we'll proceed to make predictions on the forecast data. So this step is where our model capabilities are put to the test as we generate forecasts for byte counts in the upcoming week. And by comparing these predictions to actual counts, we can evaluate the model's performance. So to better understand the model's effectiveness, we will visualize the actual versus predicted byte counts. And this plot will allow us to see how closely our predictions align with the trend or seasons or just the patterns overall and the reality of bike usage. And visualizations are powerful tools for communicating and can help us quickly grasp the performance of our model. So in the plot, we will see whether if it looks very off, the model is probably not good. And if it looks just consistent or makes sense with the historical data, then it's a quick way to see if our model is doing good or not. So once that is done, we have plotted the results. We will save our forecasted and actual byte count data back to MongoDB. So by storing this information, we can reference it in future analysis or improve our model further based on new data. So let's run this script and see the results of the visualization. I'll select all and click on run here. And just wait. This might take a couple of minutes, but after it has run successfully, and as a result, we get a plot of the actual bike counts and the predictions for the following 7 days. We can see this by navigating here to plots. We can zoom in. Here's the actual graph with the actual counts of data over time and then our predictions. This looks okay, so we'll take it as good for now. So we can also see in the console the message indicating it was successfully uploaded to the MongoDB. And again, once we get the actual values for these dates we predicted, we can use this JSON that we stored, so we can retrieve it and with the forecasted values and see how our predictions actually did. So in summary, with this script, we went through the process of fetching data, feature engineering, modeling with XGBoost, tuning hyperparameters, making predictions, and even visualizing the results and storing the outputs. So each step is critical for developing a robust model that can accurately forecast the byte counts. And this can be adapted for various time series beyond byte counts, demonstrating the flexibility and power of these methods. So now that we have successfully created our forecasting script, let's discuss how we can automate this process to run seamlessly in the future. Automation is key to ensuring our models stay up to date with the latest data, and we have a few great options for achieving this. So if we go back to the BDTI platform in the service catalog and sign in. Good. I'll first present Mage. So this is a service available on the BDTI platform, and it provides a straightforward way to schedule tasks directly. You can set up your own R, Python, or SQL scripts to run at the specified intervals, and so you don't have to worry about manually executing them. Another option available in the BDTI platform is Apache Airflow. This is the first one here. And while we haven't delved deeply into Airflow in this workshop, we did cover it in our previous session on Barcelona Air Quality, so you can retrieve the materials from the workshop in the BDTI Skills Studio GitLab, also the recording. So Airflow allows you to automate workflows by creating DAGs that define your data pipeline, and it can execute R scripts through batch operators, providing a powerful orchestrating tool for your tasks. There's also the option to use GitHub Actions or GitLab pipelines, and both of these tools enable continuous integration and deployment. And you can set up workflows that automatically trigger your R scripts whenever there's new data available or based on a specific schedule. And in this case, we probably want to schedule this to run daily since it's the frequency of update of the data source. And this way our forecast will always be up to date. In summary, we have several options for automating our forecasting script. So Mage, AI, Apache Airflow, GitHub, GitLab pipelines. And each of these tools offers unique capabilities that can help you streamline your workflows and ensure that your analyses are timely and relevant. So as you explore these tools, you'll find a wealth of documentation and community support available to help you along the way.
Excellent. Thank you, Berta. So let's summarize back what we've just seen in this demo. Right, this is the kind of the step-by-steps that we do. We set up the environment in BDTI. We went through understanding the data that we had from the API. We see how to fetch and how to store the data into the database with R. And then we build a forecasting model and visualize the results, right? Again, all the automation. It was covered in a few other seminars. So I think that was the idea, to show you the summary of what we've done today. Right, sorry, that was kind of the recap. What's next, right? So what to do after that? So let's think on our initial question. Right? At the start of the session, we posed a central question: how can Paris enhance urban mobility and promote sustainable transportation by comparing forecast and actual bicycle traffic data? Now that we've walked through the process of collecting, analyzing, and forecasting the bike traffic data, we can return to this question with a deeper understanding. By analyzing discrepancies between forecasted and actual data, we can uncover hidden trends, identify opportunities, and fine-tune the city's cycling infrastructure to better meet the needs of the citizens. We will explore some recommended actions that Paris could take based on the insights derived from this analysis. They could optimize the bicycle infrastructure, adjust the placement and expansion of the bike lanes in areas where the actual data consistently exceeds forecasts, ensuring sufficient capacity to accommodate the actual demand. They could do target promotion of cycling, launch campaigns to encourage cycling in underutilized areas where forecasting traffic was higher than the actual count data suggests, helping balance the usage across the city, or implement adaptive traffic management. We use the actual hourly data to dynamically manage bike lanes and crossings, particularly during the peak times. By comparing forecasted and actual bicycle traffic, these recommendations allow Paris to proactively enhance its cycling infrastructure, promote greener transportation options, and contribute to its broader sustainability goals. The key to success will be ongoing data collection and analysis, ensuring that the city's strategists adapt to the changing needs and behaviors of the citizens. As we wrap up this workshop, it's important to remember that the methods and tools we've explored today, from forecasting using time series models to storing and retrieving data in MongoDB, are adaptable to a wide range of public sector challenges. The key takeaway is that by leveraging data forecasting and analysis, cities can make informed decisions that optimize infrastructure, promote sustainable transportation, and improve the overall flow of urban life. Whether you are dealing with bike traffic, public transportation, or even foot traffic in pedestrian areas, similar approaches can help anticipate demand, manage resources more effectively, and encourage greener, smarter mobility solutions. You are now equipped with not only technical skills using RStudio, R Markdown, and MongoDB on the BDTI platform, but also the understanding on how data-driven strategies can directly influence urban policy and improve city planning. By integrating forecast models into your decision-making processes, you can create a more responsive and efficient city infrastructure that meets both current needs and future demands. As stated before, these slides, all the code, and all these learning materials will be provided in the GitLab repository. You will have here the link, and I think it was also shared in the chat. And now, before we wrap up, we will open the floor for any questions you might have. Please feel free to type your questions into the chat, and the team and I, we've added Alex into our call, one of our data scientists, for more experts' questions. Kim, passing the word back to you.
Yes, thank you, Jordi, and thank you very much for leading that workshop for us today. Let's jump into some questions. If you do have questions, do please post them into the chat or the Q&A widget down below. We'll kick off with a question that came in from the chat. Should we always initially include all variables in the beginning to select the most relevant variables in forecasting model? I'll hand that one to you, Alex.
So, as always, the decision depends on the problem complexity, the tools that we have, the resources that we have. And as we're talking about machine learning, the trade-off between the interpretability and the performance. So if we are including like all the variables initially, we have some pros. We have a comprehensive exploration with all the variables, reducing the risk of missing a very important variable or a variable with a high predictive impact. And we can kind of capture like global relationships. But also we can commit like a lot of overfitting, okay? It might have a high computational cost. We can have collinearity issues. And yeah, so I suggest using this when either we have enough computational resources or applying other techniques for feature selection, okay, such as dimensionality reduction and so on. Also, when we are dealing with a very large data set, where the relationships are not easy to catch or to understand just looking at some portion of the data set. And if you are using models like the random forest or gradient boosting, as the one in this use case, that can handle many features, and the same model performs an implicit feature selection. And I suggest going the other way, just adding variables incrementally. When we have a domain knowledge, for example, that we see that there is a kind of a hierarchy of importance for variables, okay? If we have a limited computation resources, the data set is small, and if we prioritize interpretability and simplicity over predictive power, we might miss some interactions, or we might be using a suboptimal set of features. But yeah, it's like the pros and cons. I don't know.
It's finding the right balance, sure.
Yeah.
So hopefully that answers your question, Ria. Thank you very much for that. Another one in is, how frequently can we fetch new data from the API?
It depends on the API, because some APIs have rate limits. So I think for this specific use case, the API allowed for frequent queries of data. So we can keep updating the data regularly and set up a schedule, but it depends on the API. So check the API documentations if there is any restriction of the number of requests, or yeah, basically it's depending on the API.
Gotcha. We have time for a couple more, I think, before we wrap up. Could we have used a different model for time series forecasting?
Yeah, yes, of course. I mean, there are a lot of good time series forecasting models. We have ARIMA. We have Prophet, that was developed by Facebook at the time. We have deep learning models such as LSTM or even if you are brave enough transformers. Each of them works differently, has its pros, has its cons. We choose the XGBoost because it's simple to understand, has great speed and good performance on tabular data. But yeah, trying different models, at least when we are starting working on a time series forecasting model, it's always a good approach. And then just select which one it's working the best, and then improve
Great.
it. Yeah.
Lovely. And finally, could we forecast further into the future, say a year ahead with the current model?
So while it's possible, we need to understand that the further away that we try to forecast into the future, the accuracy of the predictions generally decreases. And this happens with every model, okay? In this use case for XGBoost, we have some strong dependencies on short-term data. So if we want to create a forecast that is predicting, let's say, a year ahead, maybe we should add some more variables so that we can capture broader trends, or maybe some more complex techniques. I think just adding some more data that is based on a further, let's say, horizon should be enough. Obviously, there are other models like Prophet or I don't know LSTMs that may work better for such long-range forecasts, but yeah, XGBoost can do it. Just knowing that we need to add more data or more variables.
Great. Yeah. Okay, and one final one came in from the chat. It's from Enzo. He says, a key data gap in transport concerns knowing the number of people traveling per car vehicle to better measure passenger per kilometer traveled. Do you know of any solution using big data that's able to capture this sort of data with the methods you've presented today?
Ooh, that's
Good question.
quite complex. Well, I don't know. I mean, that's quite complex. Of course, you can add variables that you can try to get from, I don't know if you could read mobile phone data, so you can kind of know how many devices do you have in the car, more or less. So you could kind of guess how many people is in every car. And I'm pretty sure that you could get some public data based on the time of the day and the mean amount of people that goes into every car. But that's really complex. Of course, if you have the data, you could add that to your model and then use it as a predictor.
Right.
But that's a tough question.
My only add to this, to Enzo, I think that we are missing data, not from the data set we have right now. It's either through the image recognition, right? So having images on those counters and to check if there is 1 or 2 people on each bike,
That's another
right?
option,
The
yeah.
car, right? Or we've seen that in public transportation having weight sensors, right? So kind of guessing if, kind of the weight of the platform, that it's more for the metro and trains that they are doing like that. Having the weight of the car and knowing how many people is in there. But that was really adding additional data to the model, right? As Alex said.
Mm-hmm.
Great. Thanks so much, guys, for the questions and for the answers on our panelists. We better fly ahead to the wrap up. So if you wouldn't mind flicking to the next slide. Thank you very much for your questions. So yes, we have added a final workshop on the 11th of December. We'll be looking at natural language processing, so that should be really interesting. So do make sure that you've signed up for that one. That'll be the end of our workshops for the year, but we've got 2 showcasing events presenting some use cases and some really interesting insights from project managers of real use cases. So make sure you sign up for those as well. One on the 12th of December, and then in the new year we'll have some project owners from BDTI pilots showcasing their solutions as well. So don't miss those. You can register for them using this QR code, or just go into the website. You'll see the events section. If we can go to the next slide, then yeah. So just again, are you eligible? If you're a public administration, if you have if you are in academia or private sector with a clear collaboration with public administration, and again, if you're not sure, just reach out and we can figure it out together. So yeah, if you want to learn more, head on over to the website or email us, and make sure you sign up to our newsletter and to future events. You don't want to miss those. So I think that's about it for, that's all we have. So thanks so much for joining us again today. And hopefully we'll see you in future events. On the next one again is on the 12th of December. So do make sure you're signed up to that one. The recording and slides and everything will be available in the repository shortly. Thank you very much for your attention, and we hope you enjoy the session.